I have a module for each week, so a few, 2 meetings per module. Okay, I want to do a few more notes on problems like we had last time. So the universal set is the entire space, the entire universe. And we call it capital U. This example, U will be the set that contains one through 7. And then close your set. We'll have just one subset, A. Let's see if I can. Okay. It contains 2, 3, 4, 6. We're finding the complement of A, and that's it. I like to draw a Venn diagram, so I'm going for a sketch of the universe. Only one subset. With 2, 3, 4, and 6. Outside of the set, you have 1, not 2, not 3, 4, 4, but you need 5. 6 is inside A, but 7 is outside. The complement of A is outside of the set of A. A has a superscript C, which is the complement of A, being the set that contains 5, 1, and 7. And then close your set. Another example with universe containing 0 through 8. We have 2 subsets, A and B. Subset A contains 0, 1, 2, 3, 4, 5. A is the set, and it contained 0, 1, 2, 3. 4, 5, 6, 7, 8. Oh, wait, no, that was the whole universe. 0, 1, 2, 3, 4, 5 is in set A. And closed. E contains 0, 2, 4, 6, 8 even numbers. So I think it's a good idea to draw a sketch of your universe, and we will find the following sets using that sketch. So find the sets A intersect B, A union B, A complement and B complement. That's it. Okay, so the whole universe will be a square, and we have subsets that will overlap just in case they share common elements, which I see that they do. This is U, my full space. Subsets are inside of the space. Okay, common elements first. So I would take something to highlight the elements that both sets share. 0, both have 2, both have 4, and that's it. So in this space that is shared between A and B, we have 0, 2. Let's finish set A. We have 0 taken care of. 1 is in the set A, but not the set B. 2, right there. 3 is also here in set A. 4 is already taken care of. We need 5. And that's that set. B has 0, 2, 4. We've gotten those. 6 and 8 need to go over here. And then check for all of your elements, which we don't have the space, but I know we go from 0 to 1 to 2 to 3 to 4 to 5 to 6. We need 7. And 8. So for the intersection, it's that space right there, A intersect B. So it's in A and it's in B. This is A or B, the union of A and B. So this set, along with that set, no repeated elements, and they don't have to be in order. It can go 3, 1, 5, 0, 2, 4. Six, 8, and that's the union of those sets. Okay, A complement is elements outside of the set of A. So outside of set A is 6, 8, and 7. Or let's write it like that. 6, then 8, and 7. Yeah, okay. Checking it out, double checking. For the complement of B, we want to hide set B, which leaves 1, 3, 5, 7. Outside of this set, set that contains 1 and 3. 5 and 7. Oof. There's one more example for this topic, and then we're going to shift a little bit and do some definitions. Okay. Our universe is capital U. Has lowercase letters as elements. And the elements are lowercase e, lowercase m, little e, little m, p, g, r, y. The subsets are A and B. A is the set that contains M, Y. B will be the set that contains R. Find A intersect B. A union B. A complement. E complement. So I'm going to start with a sketch. Full space is you. Subsets are A and B. I could draw them separately since they don't have common elements, but it's okay to have them overlap. But there's going to be nothing in the shared space between A and B. We just have R over here on this side in set B. M and Y are in set A. Your other elements need to sit outside of your set. So E is down here. Got M, we need P. G, R, Y are good. A intersect B is empty. And you can write brackets, empty brackets. It's also okay to just write the empty set. So you can put curly brackets that have nothing inside. It's okay if you want to put a curly bracket and just like a comma and then another curly bracket, or you can write empty set. There's nothing in there. A union B is to take the set A with set B and what's shared. So M, Y, and R are in the union. A complement is all of the elements in your universe except for the ones in A. So everything except for M and Y, which would be R, E, G, P. So complement of A is the set that contains elements that are not in A. R, E, G, and P. Same for the complement of B, everything outside of the set B, so everything except for R, which would be M, Y, E, G, P. Oh, outside of B is M, Y, G, P. Okay. I think that's good for that topic. Okay, so I'm going to go over some new definitions. And before we do that, do you have any questions, any concerns? No, no, okay, cool, thank you. Okay, we're defining a variable, talking about different kinds of variables, which will lead us to interval notation. And next week we'll practice more interval notation. So these definitions are kind of important, but mostly we're leading into practicing interval notation. First one is a variable is a characteristic that can assume different values. It's not gonna work. We need this over here. Characteristic. I got this. My brain. Aracter. Okay, when we get there, most of the time, I'm going to pick X for the variable. So we'll use the symbol X to represent a characteristic, and X can be different values depending on what characteristic we're talking about. So let's talk about different kinds. There's kinds that are qualities and kinds that are quantities. So there's a qualitative or a quantitative. And don't worry about needing to memorize these definitions. It's just to be clear. It's clear definitions so that later as we do examples, you know what I'm talking about. Okay. Qualitative variables have values that cannot be measured. All right, so I have a few examples. One of them is eye color. Color. It's been a long day, but I got this. It can take on values like green, blue, hazel, brown, and so on. Okay, blood type. You could have blood type that's A or B or O or different combos of those. There's political party as an example. Democrat, Republican, and such. And another one I've got is profession, and so on. Okay. Next is a quantitative variable. Let's let this sink in for just a second. Okay, so quantitative variables have values that can be measured. Like a quantity. Okay, quantitative have values. And these are the kinds of values you can measure. Values that can be measured. Okay, examples. I've got time, temperature, height, weight. Let's do one more, like distance, and then just put dot, dot, dot. Cool. Okay. Next is I want to talk about how there's two kinds of quantitative variables, discrete and continuous. Before we do the definitions, we're going to draw a picture. Let's do this. Actually, I'm going to leave quantitative as a part of my picture. But put it in its own separate space, in its own square. Separate from that, we had qualitative variables. Okay, back to this side. This side, we're going to split into discrete or continuous. And the plan is to do just a couple examples for discrete And then we will spend a bit of time talking about interval notation for continuous variables. We're writing the set for a continuous variable in interval notation. Okay, let's start here. A discrete variable has a countable number of values. Or let's say discrete variable, that's good, it has a countable number of values. Okay, so I've just got 3 examples for this definition. First one, our variable is going to be x. We're going to let x be the number that you get when rolling a fair die. Number that we obtain is the same thing. That means x is going to be a discrete variable. It can be 1 or 2 or 3, 4, 5, or 6. So x is a discrete variable. X can be any value in the set that contains 1 through 6. So we're going to sketch a graph and then plot the values of x on that graph. Okay, so this is, and I'll talk a little bit more about this soon, but this is going to represent a real number line. So all real numbers are possible on this line. Let's put a placeholder of 0. And I need my, I would call these critical numbers or numbers of interest somewhere on this line. I'm going to put some extra just for fun, but you don't need extra if you're drawing a sketch. And we want to show that we're using these values with a solid dot. So we include 1 by putting a dot over 1. 2, 3, 4, 5, 6, and those are the only values of x, a countable number of values. And that's it. In the next example, I'm still using x for my variable. Thanks for being patient. We will make it to the same place where my other class made it through the notes, and then that'll be that for today. So we're doing good so far. Okay, and this one, x is going to be the number of computers that are available in a lab that has 4 computers. Kind of rewording the problem, but it's the same idea. So x is going to be the number of computers available in that has 4 computers. Okay, this means x is a discrete variable. Because either there are no computers available, there's 1 computer, 2, 3, or at most 4 computers. All of them are available. Okay, x can be any value in the set 0 through 4. And again, I want to draw a little sketch for the graph. Okay. So it's a number line, and then on that, we're going to plot values of x. Zero, 1, 2, 3, 4. I'm going to put extra just because I want to be clear with my notes, and maybe like just show that there's more numbers going on this number line. But for our variable, we just want to mark these values with a solid dot. Okay, for this last example, we're going to go straight into just talking about how x is a discrete variable. Ready to go. Let x be a discrete variable. such that x can be any value in the set in the set that contains picked 2, let's put 5 and 8 and 9. Draw a graph. So we have a number line, just one number line for one variable x. I haven't really mentioned it yet, but just to remind you that this way we're leading towards negative infinity. Over here is positive infinity. And we need 2, 5, 8, and 9 on the graph. I'm going to have my units evenly spaced out, but I will start at 2. 3, 4, 5, 6, 7, 8. And we're including 2, 5, 8, and 9 with a solid dot. And that's the end of talking about discrete variables. Okay, so we're on to continuous variables next. So a continuous variable can have, let me see, it can, we're going to say it like this. X is a continuous variable if possible values of x are in an integral. Any x can be any value in an interval. Or in a union of intervals, which we'll talk about later. We'll get to that next week. So here's where we're going to start to talk about interval notation. Okay, so for the first part of this, which I just want to let this sit here for a moment, but after this thought, we're going into a new topic. We're in interval notation now, and I want to introduce strict inequalities. Like this symbol or that symbol. Those symbols are strict inequalities. And we're going to just practice. So the first one is to graph x less than 3. Okay, there we go. First, let's just talk about what this means. So writing it down. This means x is strictly less than 3. I'm just going to put x is less than 3 and not equal to 3. Okay, it's an equal sign crossed out. Usually the slash goes like this. So not equal to 3. What you want for your values of x are numbers that make that statement true. So something like 2 is less than 3. That's a true statement. So x can equal 2. X can equal 1. X could be a negative number like negative 3. We know that x is less than 3, but not equal to 3. And it's not greater than 3. So x does not equal 4. X cannot equal 5. And keep going. X does not equal 10. Such. Okay, so you have your number line for the graph. The only number that you really need on your graph is 3, but I'm going to put some extra units. 1, 2, 3. For x not equal to 3, we're going to have an open circle right above 3. And you shade over the values that are possible for x. So we're going to shade x is less than 3. So we're going to go to 2 and 1. We're going to go this way. But do not shade values of x that make the statement false. So we're going to leave the other side unshaded. All right, next example. We will graph x greater than 8. To be clear, this is x is greater than 8. And there's no equal sign, so it's not equal to 8. Okay, again, x could be any number that is greater than 8, 9 or 10 or 20. But we don't have x equal to 8 or any number less than 8. We already have that. Numbers less than 8, like 6 or 4. Okay, that's good. So drawing a graph of x greater than 8, we'll need to plot 8 on the graph. Okay. We do not include 8, so there's an open circle. X needs to be greater than 8, so x could be 9, x could be 10. Those numbers are greater than 8. So you shade over the solution side, the side that has values of x that makes the statement true. And the other side, we don't shade. Those values of x make the statement false, and they are not solutions. Okay, next one is graphing x greater than or equal to 2. Okay, we'll write down what that means. So when you have that part in your symbol, it's a part of an equal sign. So x could equal 2. Yeah, and I do suggest working together if you guys are comfortable. Okay, x is equal to 2. Okay, again, values of x need to make the statement true. So 3 is greater than 2. It is a solution. Another solution is 4. I could have x equal to 4. X equal to 2 or 3 or 4 or so on past 2. But I can't go below 2. I can't go to 1 or 0 or to the negative side. we need a number line. And the only place you really need to mark is 2, but I'm going to put a few extra numbers on here. X is greater than or equal to 2, so you have a solid dot above 2. Because you can include that number. And this number is greater than it, like 3. Okay, so the shaded side is the solution side. And do not shade over values of X that make the statement false. One more. And then we'll do an intro to interval notation. Oof. All right, next is graphing. X less than or equal to 6. Yeah, we're gonna just write it all out. X is less than or equal to 6. X is less than 6. Or X can equal 6. Let's just start the graph. So we have our number line for values of X. I need 6 on the graph. I'm going to have a little extra so I can talk about solutions. X can be equal to 6. You do have a part of that sign as an equal symbol. So include 6 with a solid dot. Numbers that are less than 6 are 5, 4. I know that 0 is less than 6, so I'm going over here towards negative infinity and shading over all of those solutions. Don't shade over statements, or don't shade over values of X that make the statement false. Like if you come over here and you have 8, 8 less than or equal to 6 is false. That is not the solution side, just this side. And as I'm kind of thinking about it, once you plot that critical value, there are 2 sides to test, the one below 6 and the one above 6. So you just need one test point. And if that test point makes your statement true, you want to shade that side. If it makes the statement false, shade the opposite side. Okay, I just want to move, I don't want to go too into test points and stuff like that. But anyway, if you're having trouble with this, with knowing where to shade, I can try to explain it using test points. I would like to get into interval notation next. Okay, so intervals are written with rectangular brackets or parentheses. There's a little more. And let's see, two values that are called endpoints. Okay. And the smaller value always goes on the left. The larger value goes on the right. So we're going to write down that the rectangular brackets are for the less than or equal to and the greater than or equal to symbol. Parentheses are for the strict inequalities, strictly less than or strictly greater than. First one was rectangular brackets. Okay. Use parentheses for strict inequalities. Oh, like this. Or this. And I have a note, and then I have a couple of notes. So the first one. If your smaller value happens to be negative infinity, it's not a number that you can include in your set. So negative infinity has parentheses, since it can't be included. And so does positive infinity. Also want to talk about the real numbers. So in our class, if I don't tell you what the universe is, assume that it's the real numbers. So if the universe is not defined, so I don't tell you what the universe is, then just assume that it is the set of real numbers. so like, of course, numbers that you can count, 1, 2, 3, those are real numbers. Fractions are real numbers. And if you have like a decimal that has a repeated decimal, like 3.6 with a bar, that's a real number. And we will denote the real numbers with a capital R that has a double bar. Set real numbers. Double bar. So those lines that I drew, those were real number lines. It was representing all possible numbers on a number line for the real numbers. All right, so we're going to take a set that looks like the ones we had earlier today. And we're just writing those sets in interval notation. So we start the set with a curly bracket. Our variable is x. It is any value in the real numbers such that 2 is less than x, which is less than or equal to, let's go with 5. And then close the set. So x is in the universe of all real numbers. I will use a graph to help switch from this set to interval notation. We'll put interval notation here and a graph over there. I want to place 2 and 5 on the graph. I will not include 2, so it has an open circle. And actually, we're going to do some scratch work on our graph. So there's 2 parts to the problem. X is greater than 2. So we're going to start at 2, go greater than 2, and don't equal 2, so don't include it. It has an open circle. The other part is right here. X is less than or equal to 5. So you can include 5 with a solid circle, go less than 5 this way. And the solution set is the place where both statements are true at the same time. So where these graphs overlap. So you're going from 2 open to 5, which is closed. And that's the shaded solution section. I'm going to erase the scratch part. Okay. When a value is not included, or when you have that strict inequality, it's a parenthesis around 2. So it goes from 2 over to 5 as as the other endpoint, and it does include 5, so you have a square. So that's the answer right there. Let's go with orange. That's our set in interval notation. Oh, wow. We've got about 5 minutes. I'm thinking we should just call it now, come back next week, and practice these examples. I have a lot of them. So I will see you all next week.